Welcome back to our video lectures on the subject material science and metallurgy. So in the previous video we have discussed about how the materials are evolved around us, and then our course content. So what is the basic definitions of this particular subject, material science, how we have defined it in materials engineering, what does it mean and what involved in the materials engineering, and then what we discuss under this metallurgical topic, metallurgy, that we have seen in the last video lecture. In today's video lecture, we will discuss about the basics of crystallography. In today's presentation, we look at the basic definition of the crystallography, what it deals with, then the importance of crystallography in the material science. Then we will define some terminology here. So that is a basic definition of crystal. Then characteristics, we look at the characteristics of crystals. Then we try to introduce the crystal lattice. Then what are the different crystal systems that are available, that we discuss in today's lecture. Crystallography it plays a crucial role in the material science. It is a fundamental technique in material science that help researchers uncover the atomic and molecular structure of materials. If you look at the key aspect that involved in the crystallography, so first one, it deals with the atomic arrangement. So it gives information to the researchers about how the atoms are being arranged in a particular material. So that information we can get it using crystallography. Then if we come to know about the atomic arrangement, it enables us to predict the property for that particular material. So we all know that in the last class also we have seen there are properties that are dependent on the structure of the material. For example, in the last class we have discussed about allotropies of carbon. So one is a diamond and graphite. So the way how carbon atoms are arranged in the diamond and in the graphene, so that will be giving us altogether different mechanical properties to both of these materials. Diamond, we all know that it is the hardest material known, and graphene, whereas it's a soft material. So this crystallography, as it can provide information that is related to the atomic arrangement, and so it will enable us to predict the properties and we can get the control on the property of the material. Then if you look at the material development, so for any material development we have to know how the atoms in the material to be arranged in that particular system. So if we can arrange the atoms in a desired positions, so that we can get desired properties for the material. So this crystallography can help develop the materials. In the process we can identify the defects that are present in the material also. Defects such as vacancies, if there is any missing atom that is situated, or if there is a group of atoms that are missing, like dislocations or any surface defects or volume defects that are present in the material. All this information we can get it from the crystallography. Then we can also get about the phase transitions. Phase transitions, that is, so depending on a particular parameter, let us say temperature or pressure, if a material is having phase transitions from one phase to the another phase, so such kind of information also we can get it from crystallography. Then the material stability. So whether the material is stable or unstable at a given conditions like temperature, pressure, humidity and any other parameter. So whether the material is stable or unstable, how the material is going to behave. So that information we can get it from the crystallography again. Then pharmaceuticals. This crystallography helps the development of drugs, and we all know nanomaterials possess unique characteristics, and what causes that unique characteristics for these nanomaterials, that can be studied using this crystallography, basically from understanding the atomic arrangement at that particular scale will help us in understanding about nanomaterials. So this is the importance of crystallography in material science. So now let us look at some of the definitions. Let us start with the crystal. So crystal is defined as it is a solid material whose atoms, molecules or ions are arranged in a highly ordered and repeating three-dimensional pattern, and that is called to be a crystal lattice or crystal. So we will be having a regular arrangement in the material here. So that results in the formation of flat surfaces that are known as crystal faces. And these faces will be having a well-defined angles between them. So there is a regular arrangement in the material, in this particular solid material. Then it can form in various shapes and sizes, that is ranging from microscopic to the macroscopic. So it can present in microscopic level, or it can be present at the macroscopic range also. Then because of these regular arrangement, it can exhibit unique optical, mechanical and electrical properties. So it will be having unique optical properties or unique mechanical properties, or it can be a unique electrical property because of their ordered structure. So structure inducing properties. So if you look at some of the examples for crystal, so one is a rock salt in our table salt, what we use in our day-to-day life. Then we have the ice, water in the solid form. Usually it forms in the hexagonal pattern. Then we have the diamond. Diamond, we all know the arrangement of carbon atoms in the tetrahedral structure. So these are some of the examples for crystals which are having highly ordered arrangement of atoms. Then if you look at the characteristics of crystal, so as we have seen it in the definition itself, so it will be having first, that is a regular and repetitive structure. So if you look at atom arrangement in this particular figure, so this is an atom, so adjacent atoms, atom arrangement in this particular direction, atom arrangement in this particular direction, and atom arrangement in this particular direction. It is a three-dimensional array of atoms that are being arranged, and you see each and every atom is like equispaced, and they are like a regular, and it is having a repetitive structure that is in the three-dimensional space. So all crystals will be having a regular and a repetitive structure, that is one of its characteristics. Then it will be having flat faces, crystalline faces. Then it will be having the sharp angles, as you can see it in the example also. It will be having flat faces. If you look at the face of the diamond, so this is one of the faces, and this is another face, and this is another face. All these are like flat faces, but they will be having a sharp angles between one another. Then these atoms will have symmetry with respect to a particular angular symmetry, or it could be a translation as translatory symmetry, or basically a trifold or twofold. It will be having symmetry with respect to its atomic arrangement. It is also one of its characteristics. Then if you look at this is all related to your structure, the way how atoms are being arranged within the atom. Based on this, we can derive these characteristics to the crystals. Then if you look at the properties wise, so it will be having most often all the crystals will be having transparency and optical properties, where through which the light can easily pass through them, and they will be having high hardness values because of very strong bonds between the atoms. It will possess high hardness. Then most of the crystals will exhibit different colors and luster, that is purely coming out from the specific impurities that is present in its specific impurity or the defect that is present in the crystalline lattice. Because of that, different colors have been exhibited for the crystalline material. You can see ice in the water, in its solid form, it will look in white transparency color, and you can see the rock salt that is having the red light pinkish color, and then diamond is the transparency. And if you look at rubies that are in different colors, most often they will be having some specific defect or specific impurity in the crystalline in the crystal lattice, and so they exhibit different colors. And these are some of the characteristics that the crystal can exhibit. So if you look at crystalline lattice, till now we were using the term crystalline lattice. So let us first define what do you mean by a lattice, a crystalline lattice, and other terminology. A lattice or a crystalline lattice, it is a three-dimensional array of points coinciding with atom positions in coinciding with a three-dimensional it's a three-dimensional array of points that is coinciding with atom positions. You see, these are the points, right? So this is the point. These are arranged in x direction and y direction. If you look at all the Cartesian coordinates, x, y and z, all the directions in three-dimensional space, all these points are systematically arranged, and these points are being considered to be the spheres, or that indicates atom positions in the material. And this three-dimensional array of points coinciding with the atom positions, and that is considered to be a crystal lattice. If you look at unit cell, so a unit cell is a basic or the fundamental crystal unit or the building block of your crystal structure. So the fundamental building block of your crystalline lattice, and that is termed as a unit cell. So here is your example. So this is a one cube that is being considered, and this is a unit cell, we call it. So it will be basically defines the entire crystal structure by virtue of its geometry and atom positions within. So this will indicates a crystal structure of the entire material, the unit cell. It is a fundamental crystal unit or the building block of the crystal structure. So lattice points are the specific points within the unit cell that represents the positions of the atom. So these are the lattice points. These are considered to be the lattice points, which represents the positions of atoms or ions or molecules within the crystal. So these are the basic terminology that we come across as we keep on discuss about the crystallographic information of any material. Then crystal systems, based on the unit cell, the way how atoms are being arranged in the unit cell. So we can classify the crystal system into seven crystal systems. One is a cubic, then tetragonal, then we have hexagonal, then we have the orthorhombic, then we have monoclinic, rhombohedral and triclinic. We have total 7 crystal systems, and if you look at the difference between these crystal systems, so if you look at the way how we will be considering based on the 3 axial lengths A, B, C, 3 axial lengths and 3 axial angles, that is alpha, beta and gamma. So this is your axial lengths A, B and C, and here is your angle alpha, beta and gamma. So these are the 3 angles and 3 lengths and 3 angles. So based on this, we will be dividing your crystal system into 7. So the relation between these lengths and angles. So if all lengths are equal and all angles are equal, angles are equated to 90 degree, and that is considered to be a cubic system. If 2 of the lengths are same and that is different from the third one, and angles are equal, so that system is considered to be tetragonal, and it is a hexagonal system where one of its angle is like gamma is 120 degree, where all lengths are different but all angles are equal, that is a orthorhombic. Then we have all angles are different and 2 angles are same. All lengths are different but 2 angles are same and 1 is different. This is a monoclinic system. And rhombohedral, all lengths are same, all angles also same, but they are not equated to 90 degrees, and that is a rhombohedral. And we have all lengths are different and all angles also different, and they are not equated to 90 degrees, and that system is a triclinic system. And within that we have 14 Bravais lattices. One is this is a basic primitive structure in all the cases. Then we have the body center, the way how atoms are arranged within this system, crystal system. So we have classified them into 14 Bravais lattice systems. So within the cubic system, we will be having the basic cube system, then the body centered. So one complete atom is situated in the center of the unit cell, that is considered to be a body centered cubic system. Then face centered. So an atom is situated in every phase of the unit cell and center of the phase of the unit cell. So that is considered to be a face centered cubic system. Like this, in each and every crystal system, we will be having either primitive one or different arrangement of different positioning of the atoms. And we have in the orthorhombic case, we have one more case, that is a base centered one. So at the center of the base for this unit cell, you will be each case we will be having an atom situated. So that is a base centered orthorhombic system. Like this, a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have 4 here. So total 14 Bravais systems, and there are 7 crystal systems we have based on this axial lengths and axial angles. So that is what that's all about today's topic. So if you recall what we have discussed, so we have defined what is a crystallography, and we have seen that it is a fundamental technique in material science that help researchers uncover the information that is related to the atomic or the molecular arrangement or the ionic arrangement within the material. And we have started defining some of the terms in the crystal lattice. We started defining with the crystal. A crystal is a solid material whose atoms, molecules are arranged in a highly ordered and repeating pattern, repeating 3-dimensional pattern, and that is considered to be a crystal. Then some of the characteristics of crystal that we have seen, like the regular arrangement of atoms, then the symmetry, then the flat faces and sharp angles between them, and properties such as the transparency, hardness we have discussed, and the color. Then we have talked about crystal lattice, how we will be defining the lattice, and how we have defined the unit cell we have discussed. And finally, we have depending on the axial lengths and axial angles present in a unit cell, we have categorized them into 7 crystal systems and 14 Bravais crystal structures in the crystallographic information, right? That is all about today's lecture, and we will meet in the next lecture. Thank you.